equal to IF, let's call this one IFX also, is IF plus IFX. And how much is the EA? Is the RAIA plus RFIF plus 2VB plus V. So this is that's the same equation I put here, but if we have an extra rows that parallel with the surge winding. Now, I'm going to work on this one a little bit. So let's say what's the VT? VT is going to be EA minus RAIA minus RFIF. I think I replaced this one with RAA also. So let's replace this one from here. It's going to be RFX, RF over RFX plus RF IA 2 VD. Let's assume this one is almost 0. Let's assume this one is almost 0. So basically VT is going to be EA minus RAIA minus, what is it? RF parallel with RFX, right? IA. And you can put these two in the same equation, same parentheses. Keep this one in mind. Let's go. So I'm going to write it again here. We say VT right. Now, another thing. Look at the characteristic here. First of all, we know E is equal to Ka flux omega, right? If you go back, look at the flux versus IF, it was something like this, right? If we are in this form, if you are in this part, the linear part. What's the relation between the flux and the IF? You're linear, right? In the linear part. Flux is all KIF, right? Right? Let's replace it here. Right? KIF. So K times Ka is going to be constant. Let's call it Kf. If, see, there is a big if here, keep in mind. If we are in the linear part, right, instead of using this equation, we can use this equation, right? And this Kf, keep in mind, is different from this Ka. This Ka was, I think, Z over 2 pi A, something like that, right? Number of conductor over 2 over 2 times pi times a number of parallel passes, right? This Kf is different from this Ka. Keep in mind, you know. What I'm saying, if it's in the linear part, you can use this equation. Now, let's come here and use that equation. I'm going to replace the EA with that equation. So, it's going to be Vt is equal to right. Now, the next thing that I'm going to do here and IA is what? Let's put it here. IA and IL, they are the same, right? IA and I load, you know, look at the machine, load is on the very right, right? IA and I load, they are the same, so basically they're like this. The reason I'm doing this, I want to find the characteristic Vt versus IL. That's what I'm looking for. I want to plot this one. Now, let's look at it. How this one look like for the shunt machine or excitation machine, separately excited machine? Remember, it was like this. He said this is a Vt, this is a IL, right? If this one is separately excited, SE, shunt is going to be a little bit worse. This is a shunt excitation. Now, how this one looks like? And this is for constant speed. This is for constant speed, right? We assume when we plot this one, we say the speed is constant. How about here?
That'd be even worse, right?
Yeah, also, I need to do one more thing here before going there. Let me do one more thing here and plot this. Let's replace IF over there also with IA, right? We know IF, how much was it? IF was RFX over RF plus RFX, IA, which IA is IL, right? So it's going to be KF, right, times RFX over RF plus RFX, omega minus RA plus RF parallel with RFX, right? And everything times what? IF, right? Everything times IF. See, this one also has IF. This term has an IL, right? This term also replace this one here with this. It's going to have an IL, right? Now let's plot it. Vt. If IL is 0, how much is it, Vt? 0. Because all this is a constant number, right? and 0 is going to be 0. Very like this, right? So this is very different from what you have seen here. This is not very good. See how much it's changed in the load? This is not very good for a source, right? What we did like for a source, something can stay constant, right? That was what we liked for the voltage source. Look at here. How this will change with the load is not what we want, right? So my point is this is not a very good candidate to be used as a source, as a generator. But now let's look at the motor characteristic of this thing. Now let's look at it as a motor. See how it's going to look like. So let's put the circuit again together. See, what I was looking here for when we are generators, you said you are looking for VT versus IL, right? Because this is important for a generator to show how good is the terminal voltage versus the load, right? For the torque, I'm looking for what kind of characteristic? T versus omega, right? Or omega versus TL, right? So I should go look for that equation to see how it's going to look like here. Let us start here. We know T is equal to K flux IA, right? This is for every motor. And we know also T is equal to EAIA over omega, right? Okay. This is a motor, so basically this is a motor, electrical torque is like this, right? And this is a TI. This torque is equal to EA times IA divided by what? Divided by omega, the rotational speed of the machine. So we have this equation. Now I'm going to go replace EA from a similar equation like this. I'm going to go write it down and come up with a similar equation like this. Let's see how much is EA. EA is equal to VT minus the drop voltage here, right? Basically is RF parallel with RFX times IL, right? and plus RA, right? So it's going to be RA plus RF parallel with RFX times IA or IL. They are the same, right? So we have this equation. We can replace it here now. EA, I'm going to replace it over there. So T is going to be EA. VT minus divided by omega. So if we simplify this one, it's going to become VT IA over omega minus RA or IL square, right? IA square or IL square. Now let's go to, see, when I'm plotting, see, I want to plot T versus omega, right? That's what I'm looking, right? Here, what I have, VT is okay. VT is a constant voltage here, right? But what I don't like here is IA. IA is going to change with the load, right? Let's get rid of IA based on T and omega. Let's go to the torque equation. Torque equation is said T is equal to K plus IA, right? T is equal to K plus IA. Again, if we are in the linear part, so it's going to be KF, IF, IA, right? How much is IF? So it's going to be KF times RFX right? So here I can find the IA or IL, right? Let's say how much is the IA squared? It's going to be this divided by this KF. What? The KF should go this. KF shall come here. Right? So now I can go replace the IA with downward to that equation up there. Get rid of IA. So everything is going to be based on T and omega, right? So if, let me call this one number 1. Call this one number 1. So we are going to put 1 into 2. Or sorry, yes. So basically, you know, how much is IA? The square root of this, right? So place it here, and IA square also replaces from here. If you do all this calculation, I'm going to write the final answer. If you do all this kind of thing, omega is going to be VT over the square root of T RFX plus RF over KF RFX minus RF RFX plus RA over this is the characteristic of the machine. Now let's plot it. Let's plot this one, omega versus if T, let's start from